Hello, this video is to show you how you can use the Haber cycle to find lattice enthalpy. I'm going to be working this out for sodium oxide and using the values given in question 3 on page 351 of the OCR chemistry textbook. Okay, so first thing that we're going to do is start off with our elements, and you've got the formation of the ionic compound itself is going to go down there, and this is going to be the enthalpy change of formation of your compound. Every time start with that. The value given for us was negative 414, so I know that that is exothermic, so that's why I've been able to draw it going down. Now whenever we do a Haber cycle, we start off with our enthalpy of formation, and then what we've got to do is go around a series of steps from our elements to first of all atomize them, then ionize them, and then finally put them together with the lattice enthalpy. So the question in the textbook asked you just to draw the Haber cycle and show all the species at the various points and to label all of the arrows. So we'll do that, but I'm also going to mix in part B where we just put the values in as we go along. So I'm going to ionize, no I'm not, I'm going to atomize the sodium first of all. You could equally well atomize the oxygen. So we're going to go up here, and now instead of having two sodiums as solids, we've got two sodium as gaseous atoms. The oxygen is unchanged. Now, key bit, there are two sodiums, so this is 2 enthalpy change of atomization of sodium. So from the textbook, each of these was 108, so this is 2 times 108. The next thing we're going to do is we are going to atomize the oxygen. Nothing whatsoever changes about the sodium, but the oxygen goes to form 1 mole of oxygen atoms. Again, use the formula that you're given for the compound to work out how much of each of the elements you need to start off with. There were 2 sodiums, so we have to have 2 sodiums here. There's 1 mole of oxygen. Of course, oxygen is O2 in its standard state, so we had to have half a mole of it. The enthalpy change of atomization is to form 1 mole of the atoms, so this is doing that very thing. So this half O2 gas going to O gas is the enthalpy change of atomization of oxygen. The value that we're given for this is 249. Okay, at this point we have to turn these atoms, these gaseous atoms, into gaseous ions. I'm going to start with the sodium again. I just do the metal first. There's no any deeper reason for that. So we had 2 moles of sodium as gaseous atoms, so what we will end up with is 2 moles of gaseous sodium ions. We've still got our 1 mole of oxygen, but don't forget to add in these 2 moles of gaseous electrons. Now I kept saying the number 2, so hopefully you've all spotted that what we've done here is 2 of the enthalpy change of ionization for sodium. The value given in the textbook is 496, so we're going to do that. Now we've got to turn the oxygen atom into an oxygen 2- ion. This is known as electron affinity. Ionization energy, remember, is for loss of electrons to form the positive ions. Electron affinity is for the gain of electrons to form the negative ions. Now the first electron affinity for oxygen is exothermic. It has a negative value, minus 141. So actually we have to come back down. And so what we will end up, there's our 2 sodiums. We've now got an O1-, I probably just got the plus there, and 1 more electron. So this is the enthalpy change of electron affinity number 1 for oxygen, and it was minus 141. Now we've got to take that negative ion and stick these negative electrons into it, so that is of course going to be endothermic again. Try and squeeze it in here, and this is going to take us all the way up to the highest point we will reach with this, and what we've now got 2 moles of sodium 1 plus ions, 1 mole of oxide 2 minus ions, and this is the enthalpy of a change of electron affinity number 2 for oxygen, and the value that we're given in the textbook for this is plus 790. Now you can, if you want, combine these two together to get the net change that you will have here, and then just do it as one step where you say delta EA1 and delta EA2, but only try that if you are feeling really confident about these. Otherwise, as kind of clunky as this seems, it's the way that you are least likely to trip up. Now we have to go from these ions to this lattice, and this is where finding a real ruler might have helped, but never mind. So we have this very exothermic step here, and it is enthalpy change of lattice enthalpy for Na2O. So our original starting point was the elements, and we had root 1, which comes down, or root 2, which goes all the way up and round. Now, I have started doing this already to save a little bit of time in the video, but root 1, the enthalpy change formation, is equal to the 2 atomizations for sodium, the 1 atomization for oxygen, the 2 ionization energies for sodium, the 2 successive steps for the electron affinities for oxygen, and then finally we've got the lattice enthalpy there. So if we put all of these in, negative 414 equals the 2 times 108 plus 249 plus the 2 times 496 plus the negative, the exothermic 141, plus the 790, and then it leaves us with this unknown value. Now you could rearrange the equation at this point, but I always find it's just easier to get the numbers down to 1 here. There's less confusion, there's less chance to mess up in an exam situation. So I would simply do this sum here and come up with negative 414 equals 2106 plus the lattice enthalpy, and I want to get everything numerical on the left hand side, so I'm going to subtract that away. Negative 2520 kilojoules per mole equals the lattice enthalpy for sodium oxide. I hope that was helpful. Thanks.